We're going to talk a little bit about parallax and how parallax gives us distance to at least some of the stars of the sky. Let's start off talking a little bit about angular measurement. So imagine that you're standing in an open field. When facing south, you see a house in the distance, and if you turn your head and look directly east, so to your left, you will see a barn in the distance. What is the angle between you, the house, and the barn? So if you point at the barn with one arm and point at the house with the other arm, what angle do your arms make? Well, it should be at right angles. So it's going to be 90 degrees. It's 90 degrees between south and east. You see the moon on the horizon just above the barn in the east, and also see a bright star directly overhead. What is the angle between you, the moon, and the overhead star? So any point on the horizon is going to be 90 degrees away from the direction straight up, which is called your zenith. Compare your answers for the barn house angle from question 1 and the moon star angle from question 2, and are they the same? Well, by golly, they sure are. And do the angles from above tell you anything about the actual distance between the barn and the house, or the moon and the star? No, they do not. Barn and house, pretty close. Moon, far away, but not anywhere near as far away as the distant star. All right. We are often unable to directly measure distances to faraway objects in our night sky. However, we can obtain the distances to relatively nearby stars by using their parallax angles. Because even though these stars are very far away, up to about 500 parsecs, the parallax angles for these stars are very small. They are measured in units of arc seconds, where 1 arc second is 1/360,000th of a degree. To give you a sense of how small this angle is, the thin edge of a credit card, when viewed from 1 football field away, covers an angle of about 1 arc second. So tiny, tiny fraction of the sky. And then this word parsec, we'll talk about a bit more in the tutorial, but a parsec is the distance away to a star that has a parallax angle of 1 arc second. So it's like parallax per arc second. In terms of other units of distance that we've used in the class before, 1 parsec of distance is about the same as 3 1/4 light years. That's what it works out to. All right, finding stellar distance using parallax. Consider the star field drawing shown in figure 1. This represents a tiny patch of our night sky. In this drawing, we will imagine that the angle separating stars A and B is just 1/2 of an arc second. And then in figure 2, so I'll flip the page here in just a second, there are drawings of this star field taken at different times during the year. One star in the field moves back and forth across the star field and exhibits parallax with respect to the other more distant stars. Using figure 2, determine which star exhibits parallax. Circle that star in each picture in figure 2. So we'll come back to figure 1 here in a second. Alright, so which of the guys is moving? It's that one. So it's gone part of its motion from July to January. From January comes February. Now it's going to come back to its starting point. That guy and that we're going to go back to figure 1. So in figure 1, we want to draw a line that shows the range of motion for the star you saw exhibiting parallax. The drawings from figure 2. Label the endpoints of this line with the months where the star appears at those endpoints. Okay. So it is this star, and that's in July. And then the furthest it got was right next to this star, and that was in January. So how many times bigger is the separation between stars A and B compared to the distance between the endpoints of the line showing the range of the motion for the star exhibiting parallax? You can take out a ruler if you want and actually measure this. It's going to be twice the distance, conveniently. Recall that stars A and B have an angular separation of 1/2 of an arcsecond in figure 1. Consider 2 more stars, C and D, that are separated twice as much as stars A and B. What is the angular separation between stars C and D? So that's going to be 1 arcsecond, because twice 1/2 is 1. What is the angular separation between the endpoints you marked in figure 1 for the nearby star exhibiting parallax? So if the distance from A and B is 1/2 an arcsecond, then between our 2 endpoints for the parallax motion is going to be 1/4 of an arcsecond. Note, we define a star's parallax angle as 1/2 the angular separation between the endpoints of the star's angular motion. What is a parallax angle nearby a star exhibiting parallax from question 9? So 1/2 of 1/4 arcsecond is going to be 1/8 of an arcsecond. Note, we define 1 parsec as the distance to an object that has a parallax angle of 1 arcsecond, so parsec. For a star with a parallax angle of 2 arcseconds, the distance to the star from Earth would be 1/2 of a parsec. And so this is the idea that the distance in parsec is 1 over the parallax angle in arcseconds. For a star with a parallax angle of 1/2 of an arcsecond, what is its distance from us? That's going to be 1 over 1/2 is 2 parsec. And for a star with a parallax angle of 1/4 of an arcsecond, what is its distance from us? So the distance is 1 over 1/4, which would be 4 parsecs. What is the distance from us to the nearby star exhibiting parallax in the drawings from figure 2? This is your answer to question 10. So we found that it was a parallax angle of 1/8 of an arcsecond. So 1 over 1/8 is going to give us a distance of 8 parsecs. And just to remind you why it is 1/2 of the angle, I'm seeing some star from points of view of Earth that are separated in its orbit by 1/2 of an orbit around the sun. So this side of the triangle is 1 AU. That's the distance to our happy little star. And that is the parallax angle. what we actually measured is in measuring how far it went back and forth. In figure 1 is we measured twice of the parallax angle P, because it was the full amplitude of the motion. But in terms of this diagram, then what we want is half of that range of full motion. So that becomes P is 1/8 of an arc second, and therefore D is 8